All right, yeah. So thanks for coming to our meeting, Ed. If you want to share your screen and we can get started with the presentation, I guess, your background.
Okay, sure. Let me do a share screen here. Okay, guys, you guys have to quiet down. Let's see, I can do, I think, share screen. Let's see, hang on here like this. You see that, right?
Yep.
Okay, we're set to go then. Okay, Matthew, thank you very much. I see you've got quite a crowd there, and Marcel, of course, I've known for years, an alumnus, and I was down there. We gave a talk down there. It's got to be 10 years now. So I'm sure it's a new crowd. Welcome. My name's Ed Fong. I teach over at UC Santa Cruz up here. But today we're going to talk about, this is the first of our talks. We've got like 4 talks we give on various antennas, but this is a good introduction one. And it was one we did, I did this original antenna back 20 years ago almost. Now we came up with the concept, but I'll give you a little background on it and we'll go through how we make a single band antenna into a dual band antenna without elaborate parts and in a fairly comprehensible way. So anyway, with the first slide here, again, this antenna we're going to discuss, it's all over the place. You actually see it all over the internet. We first introduced in 2003, but it's in the antenna, ARRL antenna classics. It's also in the compendiums, the 2 compendiums, and I believe it's in the new, I don't have a copy of it in the ARRL handbook. So it's a pretty true tried design, pretty reliable. I think today we have over 40,000 of these out there, 40,000 over the last 20 years, tuned to various bands for commercial and ham in combinations. But we'll show you the basic technique. And you guys are all engineering students and engineers, so you can go out and do it on your own. So here we go. So here's the article on the right-hand side was the original article. You can see how old it is. For less than $10, and you can't probably do it for $10 anymore. That was back in 20 years ago, in 2003. That's the one we're going to discuss today. We've subsequently made a tri-band version of it, and then we did a roll-up version in 2003. That was another article in QST. This is the tri-band version. This is quite a challenging one. We won't talk about it tonight, but I do have a talk on this, on how we developed this. It's a 2-meter, 220, 440 version of the antenna. Very interesting specifications. No radials. It's not very tall. Here's my daughter standing next to it. It's about a foot taller than her. Easy to erect. You don't need a lightning arrestor. And this one was really done. Actually, we did this 5 years ago for FEMA. FEMA came up with this concept. We need an antenna. We're getting all mixed up. We have too many antennas in our vans, and we just got to set something up. It's got to work. It's got to work reliably. And we said, well, how about something like this? 3 bands, and they operate 3 bands, 2 meters, 220, 440. You can't go wrong. You can plug it into any radio. It won't blow up, and it's easy to erect. So that's another separate talk, but we won't discuss that today. That's a separate, takes an hour. So, and we also had to patent some of these. People started copying us. We didn't copy. The one we're going to discuss today is not patented. It just didn't dawn on me the first time to patent one of these. I thought I just shared among the ham community. Well, it turns out a lot of folks started copying it. Actually, it turns out I found out today that Comet has an exact copy of ours. Turns out it was not patented. But we, back about 2005, we saw a lot of people copying it and selling it, and they weren't even copying it correctly. When we bought them off, when my students at UC Santa Cruz buy some off, not using my name, we couldn't find a single one that actually worked right. So I didn't like that. I didn't mind them copying it, but I didn't like them copying it when it didn't work properly. They just copied our dimensions in the article and said, oh, here it is. Well, it's not that simple. Material is different. Velocity factors differ. So you're gonna, you guys, especially you guys in RF, everything takes trimming. You need to put it on a network analyzer. You got to trim it for each band and impedance matching and all that to get it to work right. So that's when we started saying, we got to patent some of this stuff, because the problem is it can give you a bad name. Ed Fong antenna, not made by Ed Fong. When it doesn't work very well, Ed Fong must not have designed very good antennas. No, that's not true. So we've patented a lot of this now. There's 2 of them. We did the tri-band one. We also did how we have a talk on how do you get gain? A lot of folks, I'm sure a lot of you folks have built in your classes or whatever, J-pole antennas or dipole antennas. How do you get gain? Right? The first thought, how about getting some gain? This thing works great. Got to get some gain out of it. So we have a discussion on talking. How do you get gain in a reasonable manner? So we're going to talk on that. But today we're going to show you how you dual band an antenna, a single band antenna. How do you get a dual band in a simple, straightforward way? So we start by saying, how about what's a good single band antenna? You know, when I was growing up 50 years ago, 60 years ago, ground planes, everyone used ground planes. I didn't know a lot about antennas. We would build a little ground plane, and maybe you guys have done it. I do it in my RF class. I do a ground plane, and then we compare it to a J-pole. And then we compare it to the dual band J-pole. So it's a pretty fun class on antenna design. But we used to use ground planes. So it turns out that's not a very good antenna, although we didn't know a whole lot 60 years ago. Ground planes are a pretty standard antenna. Today it is not. It is not at all. In fact, I'll show you why. Here's a picture I took about 3 years ago. If you guys are from the Bay Area, you know the Bay Area. This is Mount Sutro. It's in San Francisco, right in the middle of the city. This is great. This is great for coverage. Right in the middle of the city is a mountain, Twin Peaks and Mount Sutro. They have a big Sutro tower, and they have this tower for the commercial folks. Well, I took this about 3 years ago. And if you look very carefully, there's not a single that I can see. There is not a single ground plane antenna here. I tend to believe that if you were to go up there and take a look and take apart these antennas, they virtually all have a configuration or J-pole configuration, what I'm going to describe today. I'm going to describe that. I didn't invent it. A lot of folks use it. What we did was how to dual band it, because for hams, we both use VHF and UHF. That's what we're going to describe here. But it's interesting that within 20 years or even 30 years, the conversion from a ground plane antenna to a J-pole design is almost 100%. And I want to discuss it why. It's no ground radios, obviously we said that already. Because ground radios, what you find is in our old repeater antennas, where we used to use ground plane antennas. When I was growing up, we used ground planes. Those radios, after a while, they just fall off. You've got too much torque on something that hangs out horizontally. So typically what I show folks is I'll get one of our antennas here, and I just have it here in my workroom. What you see is our workroom here. You get one of our antennas, and you can hold something up vertically very easily. This is just a PVC pipe antenna, but you can't hold up something horizontally like that. It's got a lot of torque. Gravity pulls down it. It isn't just pushing down it. It's got torque associated with it. You guys are engineers, so you guys learn R cross F in your mechanical engineering class. It's R cross F. That's hard to hold up. It eventually falls down. Oh, I've got this light, our kitchen light there. Wow, that really glares. Hang on, I'm going to turn this off. Hey, can you turn off this light temporarily? Turn off that light. Oh, it really glares. Right? Yeah. We're going to go. Okay. Is that better? A little better. Our lighting's bad here, the way I have it configured. Anyway, so in this antenna we're discussing today, and I think a lot of you guys have built these, they're called J-poles. It's end-fed also. End-fed antennas do not need a lightning arrestor. And it took me some convincing for some companies when they switched over. You don't need a lightning arrestor. It's a DC short circuit. I'll show you in a while. Again, you guys should better comprehend this because you're engineering folks. Here's a dipole. Here, we used to use these on repeater ends quite often. We would have a group of them, 4 of them to give gain. Well, what's the problem with one of these antennas? It works. Ideally, it works. But if you use them a lot, in over a 5 or 10 year period, there's all these things that come up that you don't like. Number one, you got to push this up. You feed it. It's a center fed dipole. So this is about 18 inches, 19 inches here. There's a little insulator there that you don't see. The center conductor goes up one, and then the shield goes up down the other. And it can't be too close to your mass. Here's the mass. The problem is the closer you are, that mass becomes a reflector. So you have to have some object to hold on to it to 90 degrees. You would say, well, I want this to go, I want it to go further and further out because you get away from the mass. That's true. But then the torque, right? You guys went to dynamics or statics. The torque here gets higher and higher because it's R cross F. It's the distance plus the force. So the more distance, the more torque you have here. And you can't go up very far in this situation where solder is very soft. If you just solder it to copper pipe, over time, it just falls right off. We've done this. That solder doesn't hold. You have to weld it. If you're going to put it up on top of a hill or a repeater, that joint just doesn't hold. And it holds less and less and less as this antenna goes further and further out, which makes it more ideal for an electrical point of view, but mechanical, it falls apart. Now, the other problem is this. It's an open circuit. In other words, there's no DC conduction between the center conductor and the shield. It's a dipole. Goes up, goes down, there's a little insulator there. So then you need a lightning arrestor because it's a DC open circuit. If there's a lightning storm miles away, or 10 miles, or even a few miles away, millions of volts. It doesn't take much. It's an open circuit now to induce 30, 40 volts. 30, 40 volts, it goes right down through the coax into your radio. And what happens after about 40 volts? You'll burn out the front end. Most front ends are designed for about 30, 40 volts. That's about it. Otherwise, you need a lightning arrestor. What does a lightning arrestor do? You put it in series with the antenna, usually, below, sometimes on top, it doesn't matter. It's usually a gas form. And if it exceeds 30, 40 volts, the gas shorts. So it discharges the top from the bottom. And these things run $30, $40, probably more now, commercially, probably $100. And antennas run a couple $100. You spend another $100 on a lightning arrestor. Well, engineers are pretty smart, or hams are. Ham says, we don't like this lightning arrestor and all these problems like this. So what does a J-pole do? Let's see. Here's a basic J-pole. You may have built these because they come in various forms. I'll discuss this in a while. How it works. It's strictly a vertical, and it's fed with a DC short. The bottom of the antenna is a DC short circuit. So when you put your ohm meter across the center conductor and the shield, it reads 0 ohms. It cannot build up charge. That's an open circuit. It can build up charge. In other words, if there's a lightning storm, it acts like a step-down transformer in the sense, millions of volts of lightning. All it takes is about 30 or 40 volts to go down your coax and burn out your front end. But in the other design, the J-pole design, it's a DC short. Whatever, it just can't build a charge. It's constantly shorting out. So what we start out with, this dual band antenna, which you guys can build. I'm sure you have the proper equipment. You need the proper twin lead, but I'll give you the theory behind it. I'm sure a lot of you have already built it. I was introduced to this by 30 years ago, longer than you guys are old. When I first got it from my friend Danny Monticelli, I didn't know anything in 1990 about these. He just says, hey, have you ever tried these? We were using ground planes and with lightning arrestors and all this stuff. And with the radios, and that's something I noticed, radios were breaking. I used a, which antenna? Oh, I used a Hustler G7, which they still make. The radios eventually fell off. They kind of get corroded and they just fall off. But this one had no radios, and he showed it to me in a ribbon, twin lead. And I looked at it, I tried it out, I loved it. And I said, what we got to do is make it really durable. Put it into a PVC pipe, and we've got a pretty good base antenna. I did, and it worked fine. And but then we have the dual band version. that the dual band version, we've shipped well over 40,000 now. That was up to 35, well over 40,000. We felt its simplicity, its performance. We made it dual band, so it functioned quite well. And people love it. I mean, it's a pretty, you can drive, it's interesting. You can drive up and down the coast, drive to Texas and drive around, and you'll see these antennas on top of people's roofs. Pretty standard in the industry now. Again, cheap, easy to make, and high performance, very durable. Now, the problem was this. So, by the time you guys were born, dual band started coming around. Late 1990s, 2000 era. 2 meters had pretty exhausted itself. And by this time, ICOM, Yaesu, Kenwood, they were introducing dual band radios because the hams started going into the UHF region because all the 2 meter channels are already been taken up. So all these dual band radios started appearing. Did dual band antennas appear at the same time? Sure. The only problem is they wanted 100, 150. Well, that was about $100 back then. Now, good dual band antennas, commercial one, $150, $180 in that range. Hams, being hams and engineers, we didn't like this. So wait a moment. I don't want to pay an extra $100, $150 for an antenna. Is there a way of making a dual band antenna? Well, what folks found that was, hey, my VHF antenna, quite often a JPO at the time, or ground plane, kind of works at UHF. And if you guys study antenna design, well, that's exactly it. If you study antenna design, it kind of works. What is kind of works? It resonates. In other words, if you plug in your handy-talkie or your mobile working at UHF into most VHF antennas, you check, the first thing you guys do is you season ham, you check the SWR. Well, you guys being engineering students knows good SWR is necessary but not sufficient. Just because you have good SWR doesn't mean you have a good antenna. You have a bad SWR probably means you have a bad antenna. But just because you have a good one doesn't mean you have a good antenna. You could put a dummy load and that's good SWR, but it won't work well as an antenna. Well, it turns out if you look into this, and you guys probably know this, virtually all antennas resonate at their odd harmonics. In other words, if I made even a simple dipole, 100 megahertz, let's say, just make a simple dipole, 100 megahertz, that's 1.5 meters each side. 1.5 meters total. 3 meters is full wavelength. So let's say a half wave dipole. Let's say you resonate at 100 megahertz. And you get one of these little network analyzers, which I hope most of you guys have. If you're RF engineers, your professors should require this since it's $50, $60 for one. It's a really cool network analyzer. You can analyze the impedance and Smith charts and all this stuff with it, make filters and test filters. You will find that it will resonate, let's say 100 megahertz, but it will also resonate at 300, 500, 700, 900, all the odd harmonics, until it's, at some point, the components fall to pieces, right? It won't go on forever because you hit the other limitations of the types of components you're using. But clearly, most antennas will, the first odd harmonic, you usually will get a dip. In other words, 100 megahertz antenna, you will clearly see a dip at 300 and 500, and it fades after that because of the losses and all this. Oh, by the way, for questions, just save your questions in the end. It's easier that way. So, okay, you see this, and if you really work it out on the, I'm sure you guys use EasyNAC or ADS software, some of the software simulations. If you simulate it, you'll get a pattern like this. If you hold up a half-wave dipole antenna in free space, ideal, in other words, if you take this antenna, half-wave dipole, in free space, not reflectors, I just pretend you have a drive, that the generator's right there in free space, what kind of pattern do you get? Without any interferences or anything like that. It will look something like this. Here's the sky, here's Earth, here's the Earth, and here's sea level, right here, sea level. So your pattern, if you were standing here, and you got your friend with the handy-talkie standing there, he starts walking away, and at VHF, this is a VHF antenna. At VHF, you're okay. You can walk around, it goes up to about here. That's the pattern. But on UHF, and fairly liberal, right? Here's your lobe, the coverage of the lobe. But at UHF, remember I said the antenna will still resonate. It'll give you a reasonable SWR. But if you really look at the pattern, remember this is the sky up here. Hey, wait a moment, 75% of the power at third harmonic is going up into the sky. All you're left with is about 25%. So you only get about 25% of the actual RF radiating at sea level. Well, that's not good. That's 1/4 your power. So that's what almost any antenna would do. So people notice it. My radio's not blown up. That's good. The resonance is okay, but performance, after a while, you know it's not good. Repeater strong, fine, you don't have a problem. But if it's simplex or weak repeater, you really notice it. It's about, if you simulate this, it's about 6 to 8 dBs less at the third harmonic at sea level than the fundamental. Man, that's a lot. That's a lot, you know, about 1/4. So all of a sudden your 4-watt handheld's like a 1-watt handheld. Don't even bother, use your rubber duck, right? For comparison, your rubber duck would even work better. So what we wanted to do here was design something. What can you do to eliminate that? To make a single antenna with a single feed point. So it's quite an aggressive goal. One antenna, but you want to make a dual band, yet you want it simple, and yet you want it to be able to, so people can actually convert their, whatever they're using, their single band antenna into a dual band, and yet have it still work. So it has to be, we've decided it had to be simple, reproducible, and preferably no radio. So we chose the J-pole for this. So obviously we couldn't ask for any fancy inductors, you know, capacitors, or capacitors are pretty useless at UHF. You know, if you guys have taken RF engineering, a 10 picofarad ceramic might be 10 picofarads at 10 megahertz. But if you, luckily you could have a network analyzer these days, cheap, swing it up to 450 megahertz, and it doesn't look like 10 picofarads at all. It's got a bunch of series inductance and series inductance and resistance associated with it. It doesn't work very well as a cap. So you can't go think you can use one. And you know what's really bad? Even a silver mica is even better than some ceramic. I opened up an X200 and an X50. That's a diamond. I cannot believe they use capacitors for matching ceramic ones. No wonder when you actually do field tests on those antennas, they do not perform like what they should perform according to you know, a simulation. You can't use capacitors. In fact, if you open up any antenna, VHF, UHF, it has any lumped elements, you know, like a inductor, not a coil that you turn, but some kind of inductor that you buy, or a capacitor. I can't see how it can work well, because just the consistency in the losses at those frequencies. Some of them, you would have passed the self-resonance. A lot of components like these, you know, lumped elements, they have self-resonances below 100 megahertz. So that's a sure sign. If you open up an antenna, you see little lumped element capacitors and inductors, forget it. That's not a VHF, UHF, maybe an HF. So anyway, how do you make this dual band? I tried all kinds of things, but the one we came up with, I think, is straightforward. You know, experienced engineers or engineering students like yourself, you can do it and play with it and learn a lot about antennas. So here we showed the pattern. So I don't know whether you guys have covered the Smith chart in your classes or not, but you know, basic RF class, E&M class would have covered the Smith chart. The only thing you have to know, the great thing about talking to the audience here is that I know you guys are at a certain level that you should understand a lot of this. The only thing you have to know about the Smith chart here, this talk, is that it represents a full half wave if you go all the way around, and a quarter wave if you go 180 degrees. And if you're on the left side, that represents a short, which is 0 ohms. And if you go a quarter wavelength, it's infinity. And an open circuit, if you go quarter wave, it's a short. That's the only thing you have to know about here. Oh, one more thing I like to teach my students, maybe you guys already know this, the difference between AC and DC. Big difference. And the way you can compare it is they're almost complete opposites. And a lot of folks don't look at it this way. I'll give you a good example. If I gave you a block of wood, but if I ask most folks, is that an insulator or is that a conductor? I think most of you say that's an insulator. It is an insulator at DC. Obviously at AC, it's a conductor because radio waves go right through it, right? That's why you can receive radio on your cell phones inside a building. Radio waves go right through it. But let's say if I give you a piece of aluminum foil, conductor or insulator. Well, most people would say, well, it's a conductor. It is aluminum foil at DC. But what is it at AC? It's a shield, right? That's how you make a Faraday cage, right? You use aluminum foil to cover up RF. So it's an insulator at RF. So whenever in doubt, they're direct opposites, which is not that obvious. And just this concept of when I show students this 0 ohm short, right? Let me get like a quarter of this stuff. Okay, hang on. Happen to have one in my lab here. There you go. This happens to be a quarter wave stub. It's about 5 inches long, which means it's about 450 megahertz quarter wave stub. And people would say, well, if I short it at one end, what is it at the other end? Most people say, well, if you short on one end, it must be short on the other. That's DC only. At AC at 450 megahertz, it's a quarter wave. It's 1/2 around the Smith chart. It actually is an open circuit. And similarly, if it's an open circuit, it's a short circuit on the other end. And if it's a short circuit, it's an open circuit. So it's exactly the opposite. And we take full advantage of this in antenna design. That is one of the most important tools of understanding antenna design. So here's a J-pole. There's a normal J-pole. Again, I assume a lot of you folks have built these and people use these all the time. This far exceeds that of a ground plane. Ground planes have radials, you have to feed it from the bottom. Nobody uses that anymore. So what if you make it out of 300 ohm twin lead, by the way, you can also make it out of 450 ohm twin lead. Although by UHF, that's a little too wide, but VHF, it still works. Ideally, you want 300 ohms, which it's hard to find now. We special order all ours. You have to special order this stuff. But what it is 37, 38 inches. That is the half wave part. That part was this part right here. That's also about 38 inches. That's the half wave point. So normally in a dipole, you would have center fed it in the middle because that's the low impedance point. It's about 65 to 70 ohms. But then you got to feed it with coax, you split it open, you have to go at right angles so you don't disturb the pattern. You come out here and again, I discussed the further you go out, the more ideal it is, but you have to hold it up at some point. The further you go out, the better it is, but then that torque, the mechanical torque will be too much. And you only can go out a few feet. Otherwise, on a hill, you just blow it apart. In fact, most of them get blown apart after a while on rough hills. But this design here, it says, no, then that's too hard to do. We would like to end feed it. Sure, you can end feed it. But what's the impedance? Well, the impedance is low on a dipole, so you can feed it with coax. But by the time it gets to the ends, where it's radiating, that's when the voltage is high and the current is low. That says that the impedance must be high. It's a very high impedance. It's no longer 50 ohms, but it's in the several thousands of ohms. It's probably not infinity, but it's in the several thousands of ohms. And our walkie-talkies are 50 ohms. So what you need to do is somehow find an impedance transformer. Again, we go back to this quarter wave. Here's a quarter wave at VHF. You would think it's about 18 inches. It is in air. This is not in air. This is in twin lead. This twin lead we use. It's about 16 and a half inches, 15 and a quarter plus 1 1/4, 16 and a half. And why is it 16 and a half as opposed to about 18? Well, the 18 inches comes from the speed of light equals the frequency times the wavelength. Standard formula, I'm sure you learned your basic physics. C is equal to F lambda. Speed of light equals the frequency times the wavelength. That's in air. And there you use the speed of light in air is about 3 × 10⁸ meters a second. And then if you put in the frequency 146 megahertz, the lambda will come out to be about 2 meters. But now, in twin lead, in this twin lead plastic, nothing goes faster than the speed of light. All materials have what's called a velocity factor associated with it. That is, how much it slows down. The velocity factor is 1, is in air, and all other materials, it's below 1. So in other words, if a velocity factor is 0.9, that means it's 10% slower in that material than in air. In fact, this is about a little bit more than 10%. That means it slows down the speed of light when we put a signal through a little bit over 10%, not quite 20, but a little over 10%. So the quarter wave in this material for 146 megahertz or so, in this material, quarter wave is not 18 inches, but about 16 and a half in that range. Then you get a match. Then the short here equals an open there, which means the low impedance transforms to a high impedance. And the high impedance transforms right into the bottom of the antenna, which is also high impedance. And then, but this is a very clever design. I think the concepts are just, in the 1930s, 20s and 30s, they came up with an idea like this. Because they wanted an end-fed antenna, like in an airplane, right? You can't go in the center. If it's HF frequencies, you're talking 40 meters, you got to run a trail, right? You run it off your airplane, run it off a trail. So again, this is a short, and this is a short, that means a quarter wave later, it's a high impedance. So 50 ohms must be somewhere there. And sure enough, it is. At 1.25 inches, you have to find it with your network analyzer. Transform this 50 ohms right here to a high impedance to match this antenna. The beauty of this design is if you were to go with some other impedance, which we don't, but if you want to, this is just a transformer. This is a transformer at 445 or 145 megahertz. If you want to go to a lower impedance, you just lower the tap point because that's going to be 0 here. And you want to go to a higher impedance, like let's say several hundred ohms for some reason, you just go up. But we typically want 50 ohms, so it's right about 1.25. You have to play around with it. So that's how the basic J-pole works. Now, pretty easy to build. And by the way, if you slip this thing into a PVC pipe to just ruggedize it, because it's twin lead just sitting out there, then again, these dimensions are slightly smaller. Again, because it has to go through the PVC pipe, it slows down the speed of light, you have to recalculate the velocity factor. So there's several versions of the J-pole. You probably see these, or if you haven't already built one. I think, if you take an antenna design class, well, this is a cool antenna, just to understand antennas, where this is the half wave, you're making a transmission line here of a quarter wave, a short circuit again, right? Short circuit, you tap it off here at 50 ohms. And if you want to reduce the impedance, you lower this. If you want to raise the impedance, you move it up. So it's pretty cool. Again, you wouldn't make one of these today because the copper is so expensive. We actually make this, we make these in our class, you'll see it. It's actually one of our labs. You make one and you get yours to work. And yeah, usually you can get it to work. They're pretty expensive now because of the copper. The copper pipe, and that's about $40 now to make one of these, because you have these end caps, you have these T's, you have elbows. It wouldn't make a lot of sense. Maybe 20 years ago, maybe because copper was a lot cheaper, but it works. It works basically. Same concept, half wave, high impedance. You're making the transmission line here. Here's the transmission line. Here's the short. The only limitation of this design is this is limited to basically VHF. It doesn't work very well at 70 centimeters because at 70 centimeters or UHF, quarter wave at 70 centimeters, only about 5 inches, 5.5 inches. The jump here is too much. This is almost 2 inches. Just to tap off the feed point. It's already, you're already losing 2 inches. That's too much. The quarter wave is only 5.5 inches. So, and then as a transmission line, this is okay. At VHF, it's about the limit because VHF, you have to remember quarter wave is about 18 inches, and this is already a little under 2 inches. So So it's marginal as a transmission line. It'll do, but that's about the limit of it. Our twin lead's only about 1/4 inch. That works very well as a transmission line. Again, this has the same problem. It works, and if you build one, it works on 2 meters, but it does not work very well on UHF. And the goal of this talk is how do you get these VHF antennas actually work at UHF also? And how do you dual band it without any losses? So one method, I looked this up, and this is a pretty good method. The Arrow, it's a commercial antenna. They tried to put UHF into their antenna. They knew the problem. If we just left this in like this, is the regular J-pole. It will resonate at UHF, although this one is pretty wide. I think you would have trouble. But the concept is you could still probably basically resonate at UHF at its third harmonic. But what they did was they added an extra piece here, 6.5 inches. So this is the UHF J-pole, and that's the VHF J-pole. And it's all in one feed line. It gets a little bit more complicated. You can actually feed it just a single piece here, because what you don't see is you don't see little insulators in there. And you get reasonable SWR. I mean, we built this one too. We have it right here. I don't have we don't build in the lab, but we tested. We've built one, and we've also bought them. And interesting attempt. I think the SWR is very marginal on this, but the idea is that you parallel 2 antennas. You put an extra piece here, so you get the UHF and you get the VHF in one feed line. When we tested, not bad. The only problem with this antenna is that it presents low impedance at UHF. Half the energy will go into here because it still presents a low impedance. And then the other half will go into there. So what's the basic conclusion without going through all the math? It says that half your energy went into the wrong antenna because it also presented a low impedance. You didn't eliminate that antenna. And the other half is okay. So it's a compromise. Now, the other antenna I kind of want to mention is you see a lot of what's called a Slim Jim out there on the internet, and you get internet beware. You hear all these claims and everything. It's just basically a J-pole. They think that by tying the ends together there, that all of a sudden you get 6 dB. You don't get those 6 dB. It doesn't do much. It detunes it slightly. I don't see any changes in pattern or anything. It's just basically still a J-pole. And it works at UHF with the same problem, 6 dB of loss. So what did we do? Here's what I did. Now, let's go back here. I didn't mention this. So what was these dots here? That's how the voltage is distributed in the transmission line here. At VHF, this is at VHF. It's obviously 0 volts here. When this thing is working, when you measure the wave, obviously here it's a short circuit. And up here it's high impedance. That's how it transfers this wave into the actual half-wave radiator. So if you look at the voltage here, if you had a voltmeter, RF voltmeter go along this line, it would be 0 here, obviously it's short. And the voltage would gradually rise to the max, or a quarter wave. At a quarter wave, it rises to a max. So what happens here? What happens why is it that the antenna still has a low SWR at UHF also? Again, without the math. You can always work out the math later, but conceptually what happens is, again, that's a short circuit. This is a VHF feeding point. We've already determined that that's the 50 ohm point. So you fed it correctly because that's a short and that's an open. The voltage at VHF is 0 here because it's a short circuit. And it goes up gradually to a max at a quarter wave. That's a high impedance point. Max current, max voltage, minimum current. It feeds into the high impedance point. Why does it also match at UHF? Very simple explanation. Obviously, it's a short circuit here. This is a UHF signal. It goes up a quarter wave here. It's about there, right? It's 1/3 the way up, max. But it continues. That's okay. It goes back down the wave. It's right about here. And it goes another quarter wave. What's cyclic? It goes up like this. So this is like one turn around the Smith chart, right? Halfway. Now it starts all over again. What just happens that at any odd harmonic, it will come back at a peak voltage, or which means the minimum current, which means it's a high impedance point. So you can feed it. That's why the matching of that matching stub will work both at VHF and UHF. The FCC was fully aware of this, to give people odd harmonics with their licenses, because it makes matching a lot easier, dual band simultaneous matching. That's why our 220 antenna that I can present in a later talk, that was much harder. It was not odd harmonic related, so it had to be an independent antenna. But when you talk about 2 meters and UHF, they're third harmonic related, so you can do tricks like this. So what happens is, so at UHF, you drive this, it looks like this, and it peaks back out, so it's at a high impedance point. What it would like to see is a half-wave radiator, not 36 or 37 inches. It wants to see about 11 to 12 inches, depending where you want to resonate. 11 1/4 is right in the middle of the band. It wants to see about 11 1/4, 12 inches, in that UHF band. If all you had was this here, you're done. It's a half-wave radiator. The problem is at VHF, you need the rest of it. So you go back to that stub again. A shorted stub, remember, a shorted stub on one end is an open a quarter wave later. And with RG174, you would think, is it going to be about 5 or 6 inches? No, RG174 has a velocity factor of like 0.7. So it's about 30% shorter. Turns out in RG174, that's about 4 1/4, 4.5 inches. A short here will be an open here at 445 megahertz, not at other frequencies, at that resonance when it's a quarter wave. So at 445 megahertz, it doesn't see that the wave that comes through from this route here, and then of course there's a half wave pattern here. It doesn't see that. It's a high impedance at that point. It doesn't see it electrically. But at VHF, that stub is not resonant. It's not resonant. And now you're driving it with this wave, with a VHF wave right here. It wants to see about, what, 37 inches or 37, 38 inches, depending on exact resonance. You add that up, 11 1/4, 4 1/4, 17 1/2, it's about 36, 37 inches. So at VHF, it sees the whole thing. At UHF, it just sees up to here, and it's an open circuit. See, that's why, if you look at this pattern here, intuitively, why did those nodes at the third harmonic come up? It's actually a pretty simple explanation. It's because what happens is at UHF, it wants to see about 11, 12 inches and stops. But in a single band antenna, it doesn't stop, it continues. So what happens to the currents? The currents continue. When they continue, it's going to push the pattern up. So intuitively, that makes sense. The current continues radiating because it does not see a high impedance point, and it will just push the pattern up. And that's when you get this thing going up in the sky. Again, if you want to talk to the International Space Station, satellites, that's not a bad antenna, but not for talking to someone else on Earth. And then we make another version, this is the roll-up version. Here's a roll, exact same concept. We just have a coax going to a BNC connector. And the whole idea is, could you get it all on one twin lead? Yeah, you could with the, whoops. Whoops, well, hang on, got it. Oh, here, okay. Yeah, with the proper, it's a single twin lead, but you got to cut it properly, put a heat shrink tubing. You can get it all one nice, one rugged single antenna. In fact, I have this. I'll show you. You can get this whole thing in a little bag like this. Great for camping emergencies. You put a little hook on the end, and it looks like one piece, but really it's got all the cuts. You don't see it. It's got little cuts that we cover up with heat shrinkable tubing and a little quarter wave stub, all in one piece, and then it ends in a BNC connector. Now, the thing you'll notice is this roll-up operates in air. You just hang it up in the air. And this base station version operates inside a PVC pipe. You stick it into a pipe because that's to protect it, to make it a base station antenna. What you'll notice is the dimensions are slightly different again, because one operates in air and one operates in a PVC pipe. The one operating in a PVC pipe is obviously going to be shorter because the speed of light through the PVC pipe is slower by a few percent. So you notice this is 17 inches. I think this is 15 and a quarter. Yeah, so you notice, yeah, this is 16 and a quarter, a little longer. It's gonna be a little longer here and a little longer there, and then that's enough. I kept it. No, see, 11 and a quarter, 11 and a half. So it makes a difference. You got to make these little adjustments depending on whether you're in air or plastic. Yeah, so we notice this. And we notice that you figured, well, when you cover it in PVC pipe, does that kill the signal? Not by much, not if you use the proper one. Obviously, certain pipes might have little metallic materials in it, even leftover fragments, it won't work. We found the Lowell's 239901 had the best RF performance. Changes the resonance, but in terms of radiation, it was fine. And sure enough, when you start testing out this in the field, the proof is in the pudding. Here we have that 2-meter J pole, but being driven by a UHF signal. It's only about up here. This is just an HB spectrum analyzer. But if you replace that antenna with ours, with that little stub, you get about a 6 dB performance increase. That's really, really good, 6 dB, about 4x. Not that the problem is that this, a true quarter wave or half wave antenna will give you this. The problem is if you run that same signal through a 2-meter antenna, you lose about 6 dB. This is just gaining back what you have. It doesn't give you gain. It just gives you back what you lost, right? If you use a 2-meter antenna at UHF, you lose about 6 dB. What you want is gain it back. So here, now the modification we just showed you, you get back the VHF and the UHF all in one antenna. And that really suits these dual band handy talk, these Baofengs, dual band mobiles, etc. So if you actually measure this in real quantitative measurements, and you figure these numbers, how do we get these? Well, this actually is quite elaborate. This is someone's master's thesis, how you actually measure antennas in real life. You just can't go and measure them. You got to read these specs. And this is a rainy day, overcast day, and a clear day. And each day you make 5 measurements in the same situation, the same terrain, and then you take the average. And we find that if you do that, yeah, the simulating results are very close. But usually, you just take one measurement. You guys will know this as scientists. Situations that change, especially when you're trying to measure over terrain, it varies. The propagation, trees, rain, fog. You have to really specify how you measure this. So in this case, this is an average of 15 measurements: 5 in fog, 5 in the rain, and 5 in the clear. And this is the measurements we get. A standard reference quarter wave mobile. By the way, it wasn't anything fancy in the sense that the antenna range is an empty parking lot on a Sunday. You want it on a Sunday when the parking lot's empty, because during the day, if you have cars, you come back on a rainy day, the cars will be in different position. It will change the measurement. So you have to make sure it was on a Sunday, the parking lot was empty. So as a reference, you get like 24.7. This is just our standard reference quarter wave mobile. And sure enough, VHF, rubber duck, 6 dB loss. We expected that. So rubber ducks aren't very good by themselves. We recommend, if you're going to use a rubber duck, make sure you get a little pigtail on it or something. Otherwise, you do lose quite a bit. And the standard J pole, again, the standard J pole is a little better than the reference ground plane. It should be about 1.5 dBs better, because again, in the J pole, it's in the clear, and the pattern is much flatter. In a ground plane, in ground radios, the angle of radiation is a little bit higher because you have radios pulling down the pattern, not another quarter wave. in a strict vertical, you've got the other quarter wave pushing down the pattern. In a ground plane, you just have radials, and the radials are 90 degrees or whatever. They won't pull it down quite as much. So a J-pole will actually give you about 1.5 dB of gain if you design it properly. Now the disadvantage of a J-pole is it is taller. Remember, a J-pole is 3 1/4 wavelengths tall. A ground plane is only 1/4 wave tall with radials. So again, if you look at that, it's practical for VHF and UHF to go to a J-pole design. But you say, hey, this is really cool. Why can't we use this at 20 meters? Because it would be too big. But at VHF and UHF, it's very practical. And then you look at our dual band J-pole at VHF, it's fine, 23.47 or so. There's a little bit of loss, about 0.1 dB loss compared to a standard J-pole, but that's imperceptible usually. And we're pretty confident in these measurements. There's 15 measurements on 3 days. Now, let's go to how well does it perform at UHF? That's what we're trying to show here. At least here we show it's almost just as good as a VHF J-pole. And a VHF J-pole is pretty good. It's better than a ground plane by about 1.5 dBs or so. How about UHF? Same thing with spectrum analyzer set up in the parking lot. Our reference is minus 38.8 dB. This is a reference for a quarter antenna. Rubber duck, few dBs off, and depending on the rubber duck, again, at UHF, the losses aren't as high here because the rubber, if you look at UHF rubber ducks, they're 5 or 6 inches. By the way, be careful of dual band rubber ducks. You have to measure them. They vary quite a bit. But just a straight 5-6 inch rubber duck on a handy talkie. And loses maybe 2 or 3 dBs. Not as good as a ground plane, but not real bad. At least it's not like losing 6 dBs at VHF. If VHF it loses 6 dBs, remember rubber ducks are 5 or 6 inches. Quarter wave should have been 18 inches. So of course it loses a lot more. It's loaded down a lot more. Now the standard J-pole used at UHF. Now we take these measurements, it's terrible. Remember, reference is minus 38.8. No wonder the thing doesn't work when you start walking around saying, hey, this doesn't work very well. If you quantify it, it's minus 45 dBs. It is a good 6 dB off. 6.2 in this case, 6.2 dB off. Of course you'll notice it, 6.2 dB. So by adding that clever little decoupling stub, how much difference did it make? Oh, wow, it almost came right back. 38.9 and 38.8. It's almost imperceptible to a quarter wave antenna. So it's quite good. It works. It clearly works. And it's fairly simple. You just need a good network analyzer to make sure you find exact dimensions for it. And the way you do this, I tell people, we cover this in the article. The way you do is you make this part first, and then you put the 11, and then you don't worry about this. You put the 11 or 12 inches of twin lead there, and you just start trimming it until you get a good SWR. And then you have to have it going at UHF. How do you know when you have to stub correctly? You start out with 4.5 inches. And if you solder it on, if it's too long, you notice your resonant frequency will be lower. You just start trimming away until by your SWR here, whatever, let's say 445 megahertz. If you made this thing resonate at 445 megahertz without the stub, if the stub is supposed to be benign, if you add it in, it shouldn't change the resonant frequency. If it's too short, the resonant frequency would go up. If it's too long, the resonant frequency would go down, based on without the stub. So you reference it without the stub. The stub's working because it should be infinity. It shouldn't affect the antenna, except that it isolates the UHF signal. It's high impedance. So whether you solder it in or out, it shouldn't change it much. That's how you know that. Then you can just add the final 17 inches to get the VHF. So if you look at the data, it's pretty good. It's basically like a quarter wave mobile or close to it. So here's our lab here. That was the original one. That was the original 8753 back in 2008 when we were playing around with these things. Now we've got we've got the 5062 now. We have 2 of those. Those are pretty nice because it's PC based. You can play around with a lot. And we're just comparing this with the Nano. The Nano is really cool. Before we end this talk, so a lot of folks ask about the stub. We make it out of RG 174, sometimes RG 58. How good is it? It's not perfect. If you guys are experienced with RF, you know, you never can get a high impedance, and you never can get it that short. Not at UHF. At UHF, you want it way over here at 445. It's actually about over here, there. Pretty high impedance, good enough. So it's not perfect, but it is pretty stable. I put my hand around it and everything. You know, the resonant point is pretty stable. Obviously, the other points where it doesn't resonate, it does all kinds of crazy things, but the resonance is pretty good. Again, you would love it to be out here. That's pretty hard to do, but that's good enough. It's certainly enough where it does affect the antenna. And then people ask about the wire. How does that little stub act at 146 megahertz? Well, here it is, high impedance. It's not resonating, it just sits there. And a wire sits about here. So yeah, that's good enough. Because you have to remember, that's a stub resonance at UHF. But at VHF, you just want to act as a wire. I'm sure it loses a little bit because you're kind of going through the shield, but it seems to work. I mean, the losses are pretty minimal compared to the gaining UHF, gaining the UHF resonance. That's very beneficial. Let's see what else. What else do we have to say? Oh, so see, here's how it looks. So when you hang it up on a corner of a house, that's easy to hold up. If this were horizontal, you'll feel a lot of torque there. But here you don't feel any torque. The R cross F is 0. It's just vertical. So it should hold up for a long time. It's a UV protected PVC pipe. It should last quite long, I would think. And we've had these antennas up for 20 years now. They still work. See, here's the little roll-up kit that we offer. Great for emergencies. It all fits into a Ziploc bag. Here's the antenna. We also include a little 6 feet of extension. It's got, we custom make these. It's a male and a female BNC, so you can extend it. And then you can put these, we can include the adapters. They go in, so for, that's a BNC, so it goes to an SMA. And you want to do your Baofeng SMA female, you plug this and spin it in there and you reverse the gender. Okay, so other talks we have are how you get gain. And then of course we have the tri-band one. And let's see, I think, oh, here's some like tri-band radios. I know a lot of students like these. I just tell people getting into this stuff isn't that expensive anymore. I think I really like the BTEC. We give a lot of these away for raffle prizes. Tri-band radio, 128 bucks, 25 watts. The radio oddity is a little cheaper sometimes. And also these, I'm sure a lot of you folks have these Baofengs. Reconsider when you buy a Baofeng, they're about $25, $26 now. For about, this price has gone way down now. For about 30 bucks, you can pick up the tri-band version of that. It's called the UV5 x3 as opposed to UV5R. You'll get the tri-band, you'll get the 2 meters, 220 and 440 for about $30. You know, I tell folks, if you're gonna go buy a radio, buy the tri-band, it's only $5 more. And I know it down where you guys are at, you guys got 220 repeaters and a bunch of repeaters all over the place. So that we have to skip. We used to carry that, but we don't anymore. We did a grant for them. It's a really cool radio. They gave us like 200 of these as samples. So we started selling them basically because we didn't charge them for the design. It's a software defined radio. Okay, so how about questions? Hey, I'm welcome to questions. Thank you very much for your attention.
Yeah, thank you very much for your presentation. That was great. Yeah, questions. People want to shout them out, raise your hands. Go for it, DJ.
So in all the diagrams of the J poles, there is the twin lead, but it's always disconnected. So the top half of the twin lead is not present on the dipole normally. Like you just trim however much you want for the frequency you want.
You're talking about this section here.
Yeah, that section.
Okay, so yeah, that's part of the twin lead. You know, that's an original design. You know what we find? Because twin lead is expensive these days.
Right.
This part you have to keep because this is the part that you can technically, all this has to be is 11¼ inch piece of wire. Yeah, that doesn't do anything. It's just part of the twin because you have to cut it, right?
Right.
What we do on the base station is, because this twin is so expensive, we just replace this with a 17-inch number 16 wire. Now you can't do that on the roll up because it's got to be one piece. Otherwise it won't hold. So electrically, you don't need this. You don't need any of this. Right. This is part of the twin lead. But then you can't get it in one piece then. We keep this and we put heat shrinkable tubing in it so that so it looks like it's one piece. It is one piece. And it holds together, you can hang it up. So yeah, here you can replace it because it's going to go into the PVC pipe because then all that's being held there is solder.
Right.
But if you look at our roll up, it's actually held together by the twin lead. It's all one piece.
Gotcha. So the twin lead is just there for support, and that's how they like ship the
Right.
copper. Gotcha.
I didn't know that.
Thank you.
Any other questions?
I have more. I just have to find them.
What's this?
I have a comment,
Sure.
not a question, but yeah, thank you for the presentation. And this is Dennis Derrickson. I have some students build some antennas, but after this presentation, I'm gonna have them build a J-pole like what you do in your class. So
Yeah,
thank
we
you.
do that, and they really like. Hey,
Yeah, I think
so
it has a lot of concepts involved there, so that's really cool.
yes, you're the RF professor.
Well, we have several. We have Payam Neary, who was on here earlier. We have Dean Arikaki, we have myself, and then we have a bunch of students interested in that area. So
Man,
Yeah,
you guys
we-
got a lot more down there than we have up here.
I think we have a little bit bigger department too. So
Yeah, build some of these. They're pretty fun. And
yeah.
do you require your students to buy the little network analyzers, the nanos?
Well, I did when we had the pandemic. Since I was doing remote lab, I had everybody buy one. But now that we're back in our home labs, we've got quite a few vector network analyzers, and so we can have them use the one they have in lab.
Yeah, but you should encourage them to buy one that they can keep it.
Yeah, that's true. Yeah.
Only
So,
$100. I mean, it's at this price, it's as valuable as a digital multimeter, right? For an RF guy.
I've got 3 of them at home.
Yeah, they're great, right? I mean, it's amazing.
The
You know,
3 gigahertz one's especially great.
Yeah, they work very well. I mean, we've got the 5062s as our main ones, but the beauty of it is I can bring the analyzer to what I want to tune, right? A duplex or whatever. In the other case, you got to bring the equipment to the analyzer.
Yeah, they're really nice. They're really nice.
They're pretty
Amazing.
good. And yeah, have you seen the spectrum analyzer, the tiny SA?
I haven't bought one of those. How do you like that?
$50, you can't beat it. You got to buy some of our raffle tickets. We raffle one off every year.
Oh, okay. So I should go on Amazon and get my tiny SA now then?
Yeah, I mean, and the beauty of it's a calibrated signal generator.
Okay. Well, I'm gonna go do that. Right after that, I'm going on Amazon and I'm getting my tiny SA.
A 1 gigahertz spectrum analyzer, right, 30, 40 years ago, when I was a grad student, you're talking $20,000.
Okay. I'm gonna
Okay,
get my
any other
tiny
questions?
SA.
Any other questions?
So how do you set up filters for VHF and UHF if the capacitors and inductors don't work as well?
How do you set up filters?
Or do you just not really use filters? Because I know like in the shack, we have a bunch of big filters that are for the HF antenna, right? I think.
Yeah, those are,
What are those for?
So you can also do variable capacitors and inductors as well.
Gotcha.
on specific things like that. But when you get to high enough frequencies, yeah, you want to use transmission line stub segments and then microstrip kind of stuff. So like edge
Yeah.
coupled filters. But I would think those use like variable capacitors and inductors, right? Like antenna tuners or something.
Yeah, that's why you don't have antenna tuners at VHF and UHF. It's very hard to implement.
Gotcha. So you just set it for the frequencies you want and then.
Yeah, you have to have discrete components or cavities and things. At HF, you can get away with that, but not at
your
VHF.
values of your inductance and capacitance get really, really small as your frequency goes up.
Mhm.
Yeah, physically you can't do it.
Yeah, you can't have, this small of a capacitance without having a big cavity.
Gotcha.
That's why we have like big cavity filters for like the repeater and such.
I see. Cool.
But at HF, you can just have coils of wire.
Right.
Yeah, HF, you can get away with coils and capacitors. At VHF, it's very, very hard. So anyway, if you guys are interested, you're a school, so I wouldn't expect, so what we usually do is I can send Matthew, if you guys want to buy any, you guys should really build them, really. We do as a fundraiser, we sell these antennas. There's no obligation. You guys know enough of this that you could build them yourself, and you have all the equipment, obviously.
I bought one.
You bought one? Who bought one?
I bought the tri-band version. It works
Oh,
great.
does it work?
Yeah, it works great.
I know, it took a lot, it's a simple
I had-
antenna.
yeah, I
It
had
takes
a
a lot
little-
of effort to get it to work right.
Yeah, I had a little issue. It wasn't working at first. I had to take it apart. The coax solder split off inside. So
Oh, okay.
I had to solder the coax back on, but
Yeah, I mean, the concept is interesting reading the concept, but to actually build one, as you know, to try to get all three resonating just right with the materials, it takes a lot of patience. It does, but it's an interesting design. The reason why we did this for FEMA said, if you can build one antenna like this, no radio, $56, we can buy thousands from you. You're right, they buy thousands from us. So, yeah, it's an interesting design. I mean, I can send this to Matthew, you guys know, there's no obligation. You guys should. Then you should try building some of this stuff. You have any questions, give me a call, because we've been doing these for a while. I've run into all kinds of problems. Once you get them ironed out, they're pretty fun. They're pretty interesting. Any other questions?
Yeah, do you teach any class at the UC Santa Cruz main campus, or are you only the Silicon Valley?
What? I can't hear the question.
Go again.
Do you teach any class at the UC Santa Cruz main campus?
The three classes I teach are off in the extension campus in
I see.
Santa Clara.
Yeah, I went to UC Santa Cruz for undergrad.
Okay, I can't hear you. Too far from the mic.
Okay, let me walk up.
Yeah, come up to the mic. Yeah.
This is
Come up
the
to
gain,
the-
this is the gain for, it, right?
The what?
Yeah.
I don't know.
Now I can probably hear you.
Okay, yeah, I went to UC Santa Cruz for undergrad. That's why I'm asking. Do you know?
Oh, no. Yeah. I teach over at the Bowers, the Santa Clara campus.
Okay. I mean,
I looked at the tiny essays. Have you done the 4.4 gigahertz one yet?
No, I haven't.
Okay,
Hey, for $50, 900 megahertz. It's got, by the way, it's a pretty well calibrated signal generator. By the way, all these are based on the analog devices synthesizer chip. That's why they can do all this stuff. If it wasn't for that, it uses the same chip in the analyzer. It's like $7, $8. It's amazing. It's something that would have cost us thousands of dollars 10 or 20 years ago. It's pretty amazing. Okay, so I thank you for your attention, and I'm gonna go get my dinner. So email me next time you want to hear the tri-band one or the gain one, just give me a call.
Thank
Yeah,
you.
sounds good.
You're very welcome. You guys take care.
thank you.